Alright guys, so in the last video we opened up 6.1 by defining differential equations. We talked about a couple different examples, but we defined differential equations to simply being an equation involving a derivative. And then we defined the order of a differential equation to be the highest derivative involved in the equation. For our purposes, we've been mainly focusing on just first order differential equations using the first derivative as our equation here, and we're going to continue that process here in this video as well too. And then we went ahead and found a problem in which we found the general solution to it. Then we did an initial value problem in which we found a particular or a specific solution to it. And in this video, our goals are to look into initial value problems, one with discontinuity, and then two by solving using the fundamental theorem. Alright, so let's first and foremost take a look here at finding an initial value problem when there is a problem happening inside that graph, the discontinuity in that graph. So the first example that we see here, it says find the particular solution to the equation dy dx equals 2x minus secant squared whose graph passes through the point 0, 3. Alright, so let's kind of start off here for a sec. Let's look into just kind of put the discontinuity aside for a sec, and let's just dive at this differential equation and find this particular equation that we normally would by finding the antiderivative. So let's start that on off. So antiderivative of dy dx is just y, and we're going to raise the power of 2x from 1 to 2 and divide by 2. So we get x squared, because 2 divided by 2 is 1. And then remember the antiderivative of secant squared is tangent. The derivative of tangent is secant squared. So it'll be minus tangent of x, and then we would have that plus c going along with it. So let's think about this. Now we have an initial value in which the pole goes through the point 0, 3. That means when x is 0, y equals 3. So 3 equals 0 in this case minus tangent of 0 plus c. Well, kind of simplifying this on out a little bit, 0 minus tangent of 0, well, tangent of 0 itself is just going to be 0. So in the end, you're just left with c equaling 3. Okay? And so the particular solution, when this is all said and done, would be the fact that y equals x squared minus tangent x plus 3. Well, what was the point of talking about discontinuity in here? Well, think about what's happening in this particular graph, alright? The point 0, 3, it only pins down the continuous piece of the general solution, alright? So this is in general with no stipulations, but we know that tangent has restrictions. Tangent has restrictions over a particular interval. And so 0, 3 only shows us the continuous piece of our general solution from negative pi halves to pi halves, right? Our restrictions on tangent. So we just have to make sure that we take into account the restrictions on our domain, that 0, 3 really is only a thing as long as we are in between our domain of negative pi halves to pi halves, okay? So the process didn't change. We just had to add a little umph to it at the end to take into account the restrictions that we had for the general solution of our equation, okay? So let's take a look at a possible another one in here as well too. We said the second part of this video had a focus in which we were going to look into an equation in which we were going to use the fundamental theorem to go ahead and solve, alright? This is find the solution to the differential equation f prime equaling negative x squared for which f of 7 equals 3. So when x is 7, y equals 3. So let's take a look here. So f prime of x, f prime of x, what does this represent? Remember our fundamental theorem. The function is equal to, the function is equal to the integral of the derivative. Alright, the integral of the derivative. What does that look like? Well, this is what's saying by the fundamental theorem that f of x is equal to the integral when x is at 7 to whatever x's limit is. I don't know what that limit for x is. From of the function, or our derivative function of e to the negative, and you can use whatever real variable you want in here, but it has to be a different variable, all right? We'll call t squared in this case dt plus whatever that 3 is going to show us in here when it is 7, right? Because if x is 7, y will equal 3. We have to kind of account for that as well, too. So that's what our fundamental theorem actually tells us, that the original function is equal to the integral of the derivative, all right? And we go from 7 to x because we know it's at 7. I don't know what my upper limit is going to be. We're going to call it x, just because that's kind of what our main variable, independent variable is that we're dealing with in this case, okay? So you kind of look at it for a sec, and it's like, all right, well, there's f of x. I've done my job. I found my solution to the differential equation. Now, it seems kind of too simple to do it this way, right? But we have to kind of think for a sec as to what the possibilities could be. So let's take it at one step further, just a little bit. So clearly, what happens here when f of 7, when x is 7? So let's say f of 7 happens. So when we throw in 7, that means the upper limit is also going to be 7 in this case. What you're going to see here is, remember we talked about our rules for integration? If our upper and lower limit are the exact same thing, that ends up just canceling out and just shows that it's going to be 0 here. So really this is 0 plus 3, or 3 in the end. And f prime is going to end up just being e to the x squared, right? By the fundamental theorem. That's kind of what we showed here. E to the x squared is going to really be f prime of x. The integral form of the solution that we just looked at, all right, doesn't look as pretty for sure than the explicit form that we've been showing in the previous one, but it does enable us to find f of x for any value of x, all right? So we still can. Now, we can use our graphing calculator to find the actual values in this case, all right? But we don't really have to too much. Honestly, we just don't really have to take it that one step further. And so for our purposes, using the fundamental theorem, we're going to leave it right here. All right, we're going to leave it right here and just say, hey, this is what our function is going to represent. It doesn't look pretty. It doesn't even have the same variables in it, but that's okay. That is what we are going to be looking for in this case. All right? We will be practicing a little bit at some point of using our calculator as a way to kind of get a more desirable, fancy-looking function that is in there. Okay? But for now, we're good to go ahead and leave it like that. Alright, and what I want you guys to do is to give a shot to one coming on your way. Now, it's kind of just going to be up to you. Notice if we are going to have restrictions or not in the particular problem here. Okay? So let's take a look. I want you guys to give a shot. Your antiderivative, or obviously your derivative, excuse me, is going to be dy dx, we kind of simplify this, dy dx. It will be 5 times secant squared of x minus 3 over 2 times the root of x. Y equals 7 when x equals 0. Y equals 7 when x equals 0. I would like you to go ahead and solve this initial value problem, identify if there's any discontinuities in there as well too. All right, this will not have to be a fundamental theorem one. Okay, this can be a discontinuity one. So focus on the discontinuity once you solve this initial value problem. All right, in doing so, you should arrive to see that the answer will be y equals 5 times the tangent of x. Let's see here, minus x to the 3 halves plus 7 with a restriction from 0 to pi half. Okay? That's what you should get in the result for your answer. Double check it, see if you're on the same page. We'll go over it first thing, and we're on to the next one.